to have balloons at 2 or 3 different radii. Also, the phase diagram clearly shows the airflow given the initial condition, so whether the small balloon inflates a large one or vice versa. And I believe, however, that she could have conducted a deflation PR curves, and this will show us how the material constants in the theory could vary with time. And moving on to the weaknesses of theory, I believe the Gaussian distribution of chains is inaccurate and does not account for the maximum extension available, because we are dealing with a physically constrained material, and this material cannot expand continuously to infinity as is predicted by the Gaussian model. And regarding the qualitative explanation of the pressure radius curve, we need a better understanding of why there are different slopes. And finally, the material properties for different balloons should also have been investigated, because even if the balloons are from a same packet, different individual balloons may have different physical constants, and this will lead to a different PR curve. And this could make the phase diagram unstable. So moving on to the experiment. I believe the characterization setup was very good, and we are able to see how the pressure in the balloon varies using the manometer accurately. And the phase diagram can allow us to predict the airflow, which corresponds with theory lines. However, I believe from the same video, the reporter could perhaps have shown us how the radius of the balloon varies with time. So this will directly answer the question regarding the airflow between the two balloons. Also, moving on to weaknesses, I believe there is a lack of investigation for the different shapes and sizes of the balloons, because we are interested in the PR curve, and perhaps for a cylindrical balloon, there may be a region of a flat pressure across radius. So in this region of flat pressure, perhaps we do not see the two balloons phenomena. Also, regarding the duration of the experiments, we saw from the graph earlier, it was conducted around 10 seconds, and this may not verify the isothermal condition. So moving on to the discussion, I would like to discuss the qualitative explanation of the pressure radius slopes, the role of the accuracy of the spherical balloon assumption, and some experimental precautions, as well as the role of the physical constants, and finally, how different properties of materials could lead to a probabilistic approach for the phase diagram. Now I would like to invite the reporter for discussion. So, regarding the first point on the qualitative explanation of balloons, perhaps we can see here. I would like to commend the reporters and the team for showing us a very good live demo of the phenomenon. So, if we take this to be pressure and this to be radius, we know for a spherical balloon it will be something like this. Do you agree?
Yes, of course.
And this part is because the balloon area is small. So, of course, when we blow air in, we'll get higher pressure. So, okay, and then this part is because the area has increased, and so the pressure will be lower. So, however, we must note that in reality, after this point, the modulus of the balloon actually is changed, and it decreases, so we get upwards trend.
Okay, so I discussed it in my presentation that in this region, non-nidality of rubber occurs. I mean, for instance, the crystallization of rubber on entanglement has a big importance. Because of that, in this region, the stiffness would be very important, and it will increase this pressure.
I agree with you that in this case, we cannot assume rubber to be linear anymore. So we understand that from the Gaussian curve, your theory line actually goes down. But I would like to go back to your modification of the theory, because we see there seems to be exponent 5 in the one you quote from literature. You have some factor behind, yes. So what is the significance of alpha, the exponent?
This alpha?
Yes.
What we are asking about?
What is okay, so first, what is the numerical value?
Okay, so you are asking what does it mean each of these constants?
Yes, if you could. So the small a in the exponent first.
Okay, so we add this polynomial correction because it's a phenomenologically it holds this relation, and also it is the very simple correction.
Okay.
So this alpha, you know, this alpha makes this polynomial correction, and also I multiply it by a.
So does alpha change the gradient of the graph or the scaling of the graph? So like then the big A, does it change the magnitude of it? So you will increase your graph to something like this.
Yeah, so the A is moving with higher A
Yes.
to be,
Okay, so this change is characterized by A, and the gradient is characterized by sort of the exponent alpha, right? Okay, because I believe the fundamental reason for the deviation of the current theory is the...
Can I just interrupt for 1 second and just ask you, when you are pointing at your diagram, can you stand back? While we can see the diagram, we can't see what you're pointing to.
Okay.
So please stand back from it when you're making your points.
Okay.
Yeah?
I believe that the fundamental reason for this deviation in the low theory line is because of the Gaussian assumption. And in the Gaussian case...
Okay, so I can refer to this Gaussian assumption. Yes, in higher extension, also the Gaussian disturbance do not hold. It also has an correlation with the crystallizes of the rubber. Because the rubber crystallizes because these molecules are one close to another in one line.
Okay,
yes, so yes, I agree with you.
Okay, so I'd like to thank you for the clarification, because what I was trying to say was in the Gaussian approximation, there's something here, even very far away to infinity. So physically, the length of rubber is constrained, and this is why the model doesn't hold. But moving on to my next point, have you measured the aspect ratio of your balloons? Because from the demonstration, we see that the balloon shape is clearly non-spherical. There seems to be a sharp point here versus, say, a sphere.
Okay, so, can I take this? We made an experiment, and our balloons were quite spheroid.
Okay, so...
Okay, and we fitted ellipsoids to it, and
yes.
from this fitting, we obtained quite a good volume of the balloon, yes?
Okay.
And we assumed that the balloon is a sphere of this volume, and from that we can easily calculate the radius. Okay,
I agree with this method, because in the case of spheroid, there are clearly two axes. So one is like the semi-major and the other semi-minor. And in this case, we take the volume to be the same and then get the effective radius. But so I agree that the spherical balloon holds. But have you considered cases of the PR graph where perhaps it would not vary? So you get a region of a horizontal line. This part, this horizontal line, do you see this behavior?
Okay, so it remains the same here.
Yes. So this is the same. It's horizontal. Have you observed this behavior in your set?
Okay, so if we have one balloon here
yes.
and the second one here,
yes.
it would be an equilibrium point.
So
because with small deviations,
yes.
the pressure won't change. So it would be an equilibrium point, and the phase diagram will look quite the same.
Yeah, I agree that there will be an equilibrium point, which is why I brought this up. Because when we see the spherical balloon, we get this interesting increase because the pressure, the whole area is being forced outwards. However, for another kind of well-known balloon, which is a spherical balloon, the cylindrical balloon, the expansion actually will just increase the radius. So in this case, then we get this. So this is a physical reason why I brought this shape up.
Okay, so I agree with you that that for the
cylindrical balloon.
Yes, this volume would be different.
Okay.
However, it is not important if it's a cylindrical or spherical, but the thing important is the curve, PV curve.
Yes, I agree. So perhaps a reporter could have conducted experiments using the spherical balloon and verified the PV curve. So
okay, so I made experiments with different spherical balloons. The shape is not important. The PV curve is important.
The PV curve
and I
important.
changed this curve.
Okay, thank you. On my next point about because can we go to your phase diagram? I commend the reporter.
Okay, so I think we should erase this.
I commend the reporter for extensively conducting experiments on the phase diagram, because you mentioned we have 70-something experiment points. So can we go to the phase diagram, please? Yes. There are a lot of points, so this must have taken a very long time to obtain. So regarding this experiment, right, you said you used the same packet of balloons?
Yes. Okay, so I previously mentioned that I pumped 5 balloons to obtain this PV curve.
Okay.
5 balloons from the same package, and I looked on the standard deviations of these different pressures, so I somehow compared these balloons. However, I can...
Because I am concerned that even if they do come from the same package, they may still be very minutely different. And
Okay,
this
so-
difference could make the boundary unstable. So.
Okay, so I showed you these differences, and maybe you are referring to the different colors of balloon, because
So
in
the colors? No,
Yeah.
I am not referring to that.
okay, because if you have one package and balloons of other colors, actually the properties are quite different, because they use different chemicals to produce it. So if you use the same package, the same colors, the results are more correct.
So I agree with you that this is why we have differences. And why I brought this up
Yeah,
is,
this is the same color.
however, the behavior will change because at the boundary, there may be some unstable cases. So, if, for example, where the blue diagonal crosses a curve, sorry, can we go back to the earlier slide? The same balloon may, at the same radius, may now, so if, for example, if you take one balloon and inflate to the same balloon, it may deflate the smaller balloon. But on the other case, when we go to the same radius, it may be the small balloon inflating the larger balloon. Hence, there may be some instability at the boundary, and this instability will be caused by the fluctuation. So, do you...
So I talked about these initial disturbances.
Okay.
In the fifth
Yes,
slide,
so
I think.
perhaps the reporter can conduct many experiments along the boundary. So by overlaying these plots, we can find how they scatter, or even just measure the different parameters in your theory and getting a probabilistic diagram. So instead of a straight boundary, we may get some shaded area. So between, say, 10% to 90% chance of inflating. So what I mean, because in your theory, you have some constants like A and alpha.
Okay, and I have an error for this constant.
Yes, so, okay, so you take the error, like delta A and delta zeta, delta alpha, and you see how they will affect the boundary. But we can move on to the next point on. You said you conducted your experiment over around 10 seconds. Do you think this will make it isothermal? Because you have 10 seconds. So, but down here, your theory assumes the temperature does not change. But when your balloon deflates...
Okay, so what we would like to emphasize, the direction of the flow is essential, as you mentioned on your presentation. So previously, in the beginning, I have one balloon, the second balloon. This has higher pressure than this.
Yes, okay.
And because of that, the air will flow from this balloon to this. The dynamics of the problem is not essential for the initial direction of the flow.
I believe the dynamics in this case will affect the predictive power of your PR curve. So not just in the two balloons, but rather when you inflate a single spherical balloon, the time that you inflate this balloon could lead to a different, perhaps when the temperature changes near the neck,
so
when this is hotter.
Firstly, the task is about the direction, and secondly, we are not talking about the temperature in Celsius scale, when it would be change of 1 degree, about.
Okay,
so
going to have to stop you there. We are over time on this. We move on to the opponent's summary.
Okay. I would like to thank the reporter for the interesting discussion we've had. I believe the report has given us a good quantitative investigation of the rubber properties and pressure curve using the Gaussian method. However, because of the assumption that of the inaccuracies of the Gaussian approximation, she was able to quote from literature a correction factor in order to get the upwards trend at the back of a PR curve. Regarding the experiment set up for two balloons, we discussed how minute changes in each balloon's inherent properties could lead to an instability at the boundaries of the phase diagram. And although the reporter has characterized multiple balloons, she should have studied the variation in the material constants more closely and given us a spread of values, because these values will allow us to see how the phase diagram could have an instability where we have a probability of inflation rather than absolute confirmation of which balloon will expand the other. Also, she assumed that balloons from the same packet have the same properties, and that this was the cause of it.
Thank you very much. We go straight on to questions from the review team, so can we have the reporter and opponent on the stage?
Okay, so good morning, everyone. Good morning, jurors. And of course, good morning to the opponent and to the reporter. My first question is directed to the reporter. So why does the polymer length obey the Gaussian distribution in one sentence? Why
Can
does,
you ask the question again?
why does the length of the polymer molecules obey the Gaussian distribution?
Okay, so if they are not length of the molecule, but the distribution in one axis. So here I have x-axis, and here I have my molecule. And it's quite long, and
okay.
I assume
okay.
that it's
I'm
a
sorry.
random movement.
The answer, okay, I'm sorry. The second question is that the inflation speed is great, and how do you explain for the discrepancy of your experiment inflation rate and your isothermic assumption?
Okay, so you are asking about the speed of the
yes,
process?
about the temperature change. Is there a temperature change?
Okay, so as I'm emphasized here,
yes
the
or no?
initial differences in pressure are essential.
Yes or no to the temperature question. Is there a temperature change during the inflation process?
Yes, there was a task about this last year, but this change is not important
okay,
for...
it's only a yes or no question, thank you. And to both, is the inflation curve and the deflation curve the same?
No.
No, they are not the same.
Then for the phase diagram, did you base your calculations on the inflation curve or the deflation curve?
Inflation, I can explain why.
Okay.
You want? Okay.
No,
so,
thank you. No, I'm thank you.
Okay.
And the fourth question is that you said that the balloons came from the same manufacturer and you used them only for one time. And how have you experimentally verified the uniformity of the balloons?
Okay, so please skip to this slide. I took
yes
the
or
5
no?
balloons from the same package, and here you can, this pink region symbolize the standard deviation of these experiments.
Okay. Thank you. How did you measure the radius, the initial radius of the balloons?
Okay, so I filled the not inflated balloon with the water, and I looked what's the volume of the water inside. And the same method, I estimate it's a sphere.
Thank you. And this question is to both parties. First, to the opponent, please list under what conditions is her phase diagram valid? Just short answers.
I believe it would be valid if we take the same pair of balloons and inflate them to different radii.
Okay, and?
Okay, so this phase diagram was constructed for the same balloons.
Okay, and the last question to the reporter. How did you determine the fitting coefficients, for example, A, in this curve that you've deducted? How did you determine the parameters?
So So it's the smallest square kilometers. I don't know how it's exactly called.
Okay, we're going to have to stop you there.
Thank you.
Okay, reporter and opponent, sit down. You have reviewer, you have preparation time. That's time.
Okay, so good morning, audience, and dear opponents and the reporter. I'm here, my name is Jia Hongyi, and I'm a member of Team China, and here to report on 5. The task: 2 rubber balloons are partially inflated with air connected together by a hose with a valve. It is found that depending on initial balloon volumes, the air can flow in different directions. And we believe that the task is to find the P to the R versus R0 relationship and to obtain a phase diagram to describe the flow of air as of the relevant parameters. And this is a brief structure of the reporter's presentation. She began with the preliminary experiments and gave a qualitative explanation of the conditions under which the air would flow from one direction or from the other direction. She then moved to the theory, the elasticity of rubber, thermodynamic laws, and corrected her theory, especially the upward trend. And then she moved into the experiment parts where she introduced her phase diagram and explained the fatigue thing, the wearing out thing. And then she explained why her phase diagram was valid for the same balloons in the first use. Now I would like to briefly evaluate the performance of the reporter. In her presentation, there was fairly clear structure, well-prepared, and vivid demonstration. However, there was insufficient explanation of some vital parts. For example, and for the strong points, next. And for the problem understanding, we believe that she had a partially correct understanding. For example, she did not introduce the partially inflation, as well as she used a thermodynamics approach, which we believe could allow for the variable temperature. And the weak point is that she did not investigate the equilibrium situation, which we believe is a missing part. Her theoretical model was based on a microscopic perspective, and she added the correlation part, which we really appreciate. And the weak point is that the isopromic process is not guaranteed because